We mentioned that any linear transformation, L, that takes Rn into Rm can be written in the form of a matrix times a vector where A is a fixed m by n matrix. So any linear transformation you can think of that takes Rn to Rm, I can find a matrix that we can multiply every vector in our vector space Rn by on the left and get a vector in Rm. Another way to think of this is any matrix that you come up with. So if you say something like 1, 2, 3, 4, 5, 6, 7, 8, 9, this matrix represents a linear transformation from R3 to R3. This is a 3 by 3 matrix. This number right here tells us that we can take R3 into R3 by multiplying any vector in R3 by this matrix. So any matrix you come up with, that is a linear transformation from a vector space Rn into Rm. So again, if let's say A is, I think we did this one in one of the videos. This is a 3 by 2 matrix. So L would take R2 to R3. And in fact, we wrote this out, I think in the first video. We said that L of x1, x2 is 1, 1, 1, 1, 1, 1. x1, x2, which is equal to x1 plus x2, x1 plus x2, x1 plus x2, and this is a linear transformation. So any matrix you want to think of, put whatever you want here. Or if you can find a linear transformation, you can tell me what this is. I can find you a matrix that sends my vectors to that vector here. So the question now is, how do we find this matrix A if I tell you the linear transformation? So let's let L take Rn to Rm, and it's a linear transformation. And we just said there exists a matrix A that's m by n, where L of our vector v, for all v in our capital V vector space, is equal to that matrix times v. How do we find A? So Rn has a standard basis. And we're going to call that standard basis, we've seen it before, calling it E. And it consists of the vectors E1, E2, E3, all the way to En, where EI is 0 everywhere except in the ith spot. These are dots here. Maybe I can make that a little clearer. So this is the ith spot, is where we have a 1. So just to be really clear, R3, the basis would be E1, E2, E3. which is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so for Rn, we always have this standard basis. So how do we find this matrix A? All we need to do is we need to plug in our standard basis vectors into our linear transformation. And what we get out will make up this matrix A. So let me write that down. So we have L of V is equal to A times V, where A is the matrix A1, A2, dot, 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 AN, with AI equal to L applied to these EIs. So what you're going to do is you're going to take each EI, so E1, I'm going to plug it into L and see what I get. And what I get I'm going to put here as a column vector. Then I'm going to take E2 and plug it into L and see what I get and put it here and continue that process. Let's look at an example. So here I have the linear transformation that's taking R2 to R4. And you can see that what I'm going to do is I'm going to take x1, x2 and send it to the first entry as I add these two together. The second entry is I multiply this one by 3. The third entry is I just write x1, and then the fourth entry is x1 minus x2. Okay, so L of V for any V in R2 is equal to a matrix A times V. And what size is this matrix? Well, A is going to be a 4 by 2 matrix. This 2 corresponds to this 2, and this 4 corresponds to this 4. Now, what is this 4 by 2 matrix? This is going to be, well, first let's recall for R2, we have the standard basis, 1, 0, 0, 1. And be careful here. Keep them in the correct order. If you switch them, your matrix is going to be different. So we're going to keep this in an ordered basis, and we're always going to start with E1 first, and then E2, E3, and so on. Okay, so we're going to take, let me write this, this is E1 and this is E2. I'm going to take E1 and plug it into L. And then I'm going to take E2 and I'm going to plug that into L. So let's do it. Let's see. L of E1 is L of 1, 0. So what does that map to? Well, the first thing is 1 plus 0, which is 1. Then I take 3 times the second entry, which is 3 times 0 or 0. Then I keep this one. And then x1 minus x2, that's a 1. Okay. What is L of E2? Ooh. Let's apply the linear transformation. So this number plus this one, so 0 plus 1 is 1. Then 3 times x2, so that's 3 times 1 or 3. Then we keep x1, which is 0, and then we take x1 and subtract x2. Okay, so that's a negative 1. So now let's write our matrix. A is going to be the matrix 1, 0, 1, 1, 1, 3, 0, negative 1. And I put this line here because I have a line here, but remember in a real matrix we don't have that line. That's just to help us visualize it. I claim that this is the matrix A. All right, how can we check this? How do we know for sure? Let's put in a test vector. So I'm going to erase this stuff so I have a little bit of room. And let's come up with a vector, v. I'm going to use the vector 2, negative 4. What happens if I plug this into L? So remember, this is our mapping. So we're going to add these two together. So I get a negative 2. 3 times this one, negative 12. We keep this one, so this is 2. And then we take 2 and minus a negative 4, so that should be 6. So V is sent here. Well, let's see if L of V is equal to A times V. So I'm going to take this matrix 1, 1, 0, 3, 1, 0, 1, negative 1, and I'm going to multiply it by this vector 2, negative 4. What will we get? Well, remember that we take 1 and multiply it by 2 and a 1 multiplied by negative 4, add those numbers together. We're going to do it for each row. So this should be a 4 by 1 matrix. So this is 2 plus negative 4, which is negative 2. 0 times this one plus 3 times this one, which is negative 12. 2 plus 0. And 2 minus a negative 4, which is 6. So this is equal to this, which is really nice. So we've shown that for this particular example, and it works for all examples, you can find this matrix just by plugging in the basis vectors, the standard basis vectors, into L. Now, suppose that we have a vector space V and a vector space W, and these are not necessarily Rm and Rn. Is it possible to represent L as a matrix? So what I'm asking you is, can we do something similar where we have a matrix times a vector? And the answer is yes.